Well, I'm taking a risk today because this is during conference hours, but no one wants to talk to me. I'm just kind of advancing towards this concept, trying to close an idea down from the Walter Lewin video. Hopefully, I haven't caused too much issues, but basically, what we've been doing is we've been talking about rotational dynamics, although we've really emphasized torque and moment of inertia. Next week, I'll start working through some examples as far as videos talking about rotational dynamics, okay? So don't feel like you are just getting the minimal from me. I will go back. Next week, we're going to basically do these yellow parts, right? 8.5, 8.6, problem solving and rotational dynamics and rotational kinetic energy, okay? But I'm going to talk a little bit about kinetic energy right now. Just so we can explain why do objects of the same type, right? Why do objects of the same type, regardless of mass or their radius, roll down a hill at the same rate? So let me see if I can get that to pop up. Okay, so down at the bottom, this whole time, and you guys still have that handout that has linear quantities and over to rotational quantities. If I had the linear kinetic energy, just a box moving, right, I'd have 1/2 mv squared. And we're starting to just see this exchange, right? This exchange of, if I have velocity, I have rotational velocity. If I have mass, well, it's going to be inertia, okay? Now, what I want to talk about is an object can have rotational kinetic energy just sitting there, right? If I had my bike wheel, which I must have left that in the other house. If I start my bike wheel spinning, guess what? It just has rotational kinetic energy. But what if my bike wheel were rotating and translating? It would have both kinetic energy that's translational or linear, but also rotational. That is an explanation as far as, I don't know if anyone's done this, I'm too chicken to do it, riding a bike without any hands. Those tires have the mass pushed out to the edges, correct? Right? And they have the most rotational inertia. And they also want to stay in track. Objects want to stay in linear motion. So that's what's kind of keeping you steady on your bike. Although I'll never do that. I don't trust it that much. But let's talk about the different energies. I can have translational and I can have rotational at the same time. Okay? So in state one, before we release it, what kind of energy do we have? We've got gravitational, and that's it, right? It's not moving, okay? It just has gravitational. Now over here, right, down here it is moving. I've got UG equals 0 now. There is no gravitational because it's at the bottom of the ramp. But I've got kinetic energy linear, it's translational, mv squared. I also have kinetic energy rotational, 1/2 I omega squared. Okay? So, what I'm going to do is, we'll go over here, mgh, doesn't really matter, the h. I've got energy 1 equals energy at state 2, so mgh equals 1/2 mv squared plus 1/2 I omega squared. Now, some of you are probably like, hey, that doesn't work, nothing cancels out. I'd like to cancel mass out. I'd like to cancel out radius, but there is no radius in there. But let's take a little deeper look. Let's designate, right, these shapes, okay? Let's make it, right, a cylinder. What was that? 1/2 mr squared. Is that accurate? If it is a cylinder, this is how I would calculate its rotational inertia, correct? So I equals 1/2 mr squared. So I'm going to replace that. Now look at this. There is no r, but I'm putting an r in there. But apparently when I had the same shape, the radius, whether it was a big cylinder or a tiny cylinder, didn't matter either. So guess where the r comes from, right? So if I did the omega out here, and I'm going to do that in different color if I can, right? V equals omega. I guess I have a capital R, right? So omega equals V over R. I'm not sure if you can see where I'm headed. Okay, let's do this. Let's substitute, right, this down here and this in there and see what happens. So MGH equals 1/2 mv squared plus 1/2 times 1/2 mr squared. And then I've got basically omega squared, right, which is v squared over r squared, right? So I just, omega squared, I squared that, so I skipped a step, right? So now, guess what starts canceling out? What doesn't matter if I have two different sizes of cylinders? Or what if I had two different sizes of spheres? Okay, or what if I had two different masses of spheres or two different masses of cylinders, right? And each one mass cancels out. I think that's one of the coolest parts of physics is how much the principle, they've developed these relationships, right? A relationship, an equation, right, between mass, acceleration due to gravity, and height, how much energy it has, and then mathematically it just cancels out, right? And we can see it occur. Okay, now, so this is telling us that if I have two different masses of the same shaped cylinder, they will go down, right? They will have the same speed, right, at the lowest height, okay? So they have the same speed, or achieve the same speed. Now, what about radius? We can see right here, radius squared cancels out also. So what are we left with, right? GH, 1/2 v squared plus 1/4 v squared. So if I wanted to find my speed, right, I could combine, what is that, 3/4? 3/4, right, v squared, g and h. So my height is going to correlate with my speed. There's nothing related to distance. There's nothing related to as far as how far it travels. It's going to have that same speed at the end. And there's nothing related to its radius, as long as it's the same shape, right? That could have been an mr squared, correct, for a thin hoop. That could have been, what is it? Is it 2/5 for the cylinder or the sphere? It could be spheres. They'd all end up canceling out anyways. So I'm hoping this explanation kind of ties in with our understanding of different rotational inertias for different shapes, but when it's the same shape, right, when it's the same shape, why mass and radius don't matter. Anyways, happy Friday. All I have for today's folder is videos and a pros and cons, so I hope you watch those. And again, next week we'll get more into working through examples. I know you guys appreciate those, okay? And really that homework sheet, that's kind of our goal through the week. And if I find anything good to get concepts, I'll add that. But ultimately, I think we're going to be working on homework. Okay? Hope you're well, and I hope to see you soon.